Okay, this is the first hour of Physics 1B for October 20th. Okay, last time we met, we were talking about this equation right here that we derived. And what it says is that there's a connection between temperature and kinetic energy, so we're going to start with that tonight. So there's a couple other equations that we had from last time that we'll bring up again. But yeah, that's one of the things we figured out was that the faster that gas molecules move, the higher their temperature is. And if you have cold air, it's going to have kind of a low velocity. And if you have hot air, the molecules are going to have a high velocity. In fact, when you were outside on a cold day, like, tonight it's kind of cold, right? If you go outside and you feel cold, one way you could interpret that is that the air that's around you has molecules that are moving slowly compared to the molecules in your skin. So your skin has a certain temperature, right? And when those cold molecules hit your skin, the cold molecules gain some energy from your skin, where the molecules are moving faster, and the molecules in your skin lose some energy from the cold molecules hitting them. Yeah, it's all about how fast they're moving. So slow-moving molecule hits a hot-moving molecule, the hot-moving molecule slows down, and the cold-moving molecule speeds up a little bit. Or you can just say that the person's skin gets a little bit colder, right? And that's what's contained within this idea right here. Now, one thing that we can do is we can solve this for the velocity and take the square root of it, and we could generate something that's called the RMS velocity. So we'll do that over here. We'll derive this equation. So if we look at this equation here, we can solve this so we have 1/2 mass. This is the mass of a single atom or molecule. You take v squared, we take the average of that, and we say this is equal to 3/2 times kb. That's the Boltzmann constant. Just to remind you from last time, the Boltzmann constant is 1.38 times 10 to the negative 23 joules per Kelvin. It also happens to be equal to the gas constant R divided by Avogadro's number. Okay? And what we can do is we can solve this for this. And if we do that, we get that v squared average is equal to, the halves cancel out. So you get 3 kBt divided by little m. And it turns out if you take the square root of the average of the squares of the velocities, then that generates something that we call the RMS velocity. So we call this RMS, VRMS. It stands for root mean square. It also shows up a lot in alternating current in Physics 1C. We talk about RMS voltage and RMS current in that class. So root mean square, right? So you've got the square of the means, or the mean of the squares. I'll put this up here. RMS stands for root mean square. The square root of the mean of the squares. Okay. And it happens to be equal to the square root of 3 kb over m. But we can write this in a slightly different way. So we can use this replacement. We can replace kb with r over na. So this also happens to be equal to 3 times r times t divided by Avogadro's number multiplied by the mass of a single molecule. And if you think about what this represents right here, if you take Avogadro's number, the units on Avogadro's number, so look at this, so Na times m, this is the same thing. Avogadro's number represents the number of atoms per mole, right? And mass, in this case, is the mass of a molecule, right? So this would be basically kilograms per atom or per molecule. And then when those cancel out, you end up with kilograms per mole. And when you talk about kilograms per mole, that's what we call molar mass. This is the thing that's read off of the periodic table, molar mass. So that means that Na times N is equal to molar mass, so we can plug that in here. So you have 3 RT divided by molar mass. Okay? So VRMS then can be written in one of these two different ways, either as 3 times Boltzmann constant times absolute temperature over the mass of a single molecule, or 3 times the gas constant divided times temperature, still absolute temperature, divided by molar mass. I think this one's usually easier to use. But either one works, depending on what you want to find. Either equation calculates the same thing. Okay. So what I'd like to do now is to just say, let's do a quick calculation of what is the RMS velocity of a molecule of hydrogen gas, okay? And let's say that we do it at 300 Kelvin, okay? We want to find the RMS velocity of hydrogen gas at 300 Kelvin, okay? So a couple things that we need. We know the temperature, 300 K. We know R, which is 8.31 joules per mole Kelvin. And now we need molar mass. So to find the molar mass of H2, what we're going to do is we're going to go to here. We're going to go to the periodic table. There it is. And we're going to look at H. And we see on this periodic table, H has a molar mass of 1.008. But hydrogen gas is a diatomic gas. So we're going to use 2 times this number. Okay, so the molar mass is going to be 2 times 1.008. And that's in units of grams per mole. Mole. Putting all this stuff together, we have VRMS is equal to the square root of 3 times 8.31 times temperature, which is 300 Kelvin, divided by 2 times this is going to be 2.016. But this is in grams per mole, so to get it in kilograms per mole, I'm going to multiply by 10 to the negative 3. That'll make it kilograms per mole, because that's basically the same thing as dividing by 1,000. And 10 to the negative 3 times kilo is 10 to the 3. These basically cancel out then. So if you do this, what do you get for the RMS velocity if you do that calculation? That's what I get. You all agree? Why did you get something different than me? I mean, it's close, but what did you use? Did you use 8.3 instead of 8.31 or something? What did you round off that I didn't round off, Ryan?
Yeah, I did 8.3 instead of 8.31.
Oh, okay, that's fine. All right, so something like 1926. Now, we can say something about something interesting about this. So, when I tell you that the root mean square of the velocity for hydrogen gas is this, right? You know that some of the molecules are actually faster than this. Some of the molecules are slower than this. And if we were to plot the velocity on the y-axis, sorry, the x-axis right here, versus the number of molecules, right, that actually have that velocity, then you're going to get something, for those of you that have already done the lab this week, you're going to get a Gaussian. Looks something like this. And the mean velocity is right here. And the RMS velocity is usually slightly higher. Okay, so this would be VRMS right here. But the point is that a lot of the molecules are going to have larger velocities, right? Some of the molecules out here are going to have velocities that are way higher than VRMS, and some of the molecules down here are a lot colder, and they'll have a velocity much smaller than VRMS, right? Now, on the Earth, you may have calculated when you're in Physics 1A something that's called the escape velocity. The escape velocity on our planet is about 11,100 meters per second. Call it 11,000, right? The RMS velocity for hydrogen is about 2,000 meters per second, right? And if you look at the equation for RMS right here, you notice that in the denominator down here is the most important part about determining velocity. So say 300 Kelvin is like the surface of our planet, right? And the temperature, let's say, of our atmosphere, right? R is something that's the same for all the molecules on the planet. And the only thing that's different is this number down here. The smaller that this number is, the bigger that the RMS velocity is going to be, right? So molecules that are heavier than hydrogen would have an RMS velocity that's smaller than this. Would you all agree with that statement? Something like oxygen, for example, O2, has a molar mass of like 32, so it's going to be a lot slower. We're going to calculate that it's about 500. It's about 4 times slower than this. So, what does that mean? Well, on our planet, the escape velocity is 11,000 meters per second. That means any particle on the surface of our planet that can reach this speed will escape the planet's atmosphere, okay? No matter what direction it's moving, if it's moving this fast, it will eventually escape the atmosphere, okay? Now, when you consider the way that these Gaussian distributions happen, what happens is that some percentage of the molecules will be up in this region right here, and the velocity over here is probably greater than 11,000 meters per second, at least for some of the molecules. Is going to be greater than 11,000 meters per second. So what that means is that over time, on the surface of the Earth, the hydrogen molecules just basically tend to escape the planet because they're all moving too fast. On average, they're not moving fast enough, but that means that some of them will be moving fast enough, and eventually all of them will have, at some point in time, the ones that are down here that are really slow will eventually be moving this fast, just due to random interactions with other things. So all of the hydrogen has basically boiled off of our planet. All of the helium has basically boiled off of our planet. And the only things that our planet is big enough to hold on its surface are the heavier gases. That's why our atmosphere is made up of stuff like nitrogen, which is very heavy, oxygen, carbon dioxide. I think those are the big three, right? Nitrogen, oxygen, carbon dioxide are the main things that make up our atmosphere. They're all heavy gases. And that allows them to actually stay on the Earth without escaping from the planet. You could do the same calculation for something like Mars and something like the Moon. The Moon and Mars are much smaller than Earth in terms of their mass to radius size. They're much less able to hold an atmosphere on their planet. So the Moon basically has no atmosphere because almost any gas can escape from it. And Mars has a very, very thin atmosphere because it has a lower escape speed, so still a lot of things can escape from its surface. But there are places in our solar system where you have a planet that's big enough to even trap hydrogen. Do you know of any of the planets in our solar system that have a lot of hydrogen in them?
Guessing the gas giants?
The gas giants, which is Jupiter and Saturn, right? And maybe Uranus is also a gas giant. I don't know. My astronomy is a little outdated when it comes to the planets. But the gas giants, like Jupiter, are mainly composed of hydrogen and helium because they're big enough to actually hold hydrogen and helium on their planet. Just to show you, the escape velocity on Jupiter is 5 times as much as what the escape velocity is on Earth. It's about 60 kilometers per second. And with that really, really high escape speed, it makes it less probable that a molecule like this could reach a speed of that size. Maybe like a very, very, very small percentage have a speed that big. And this percentage is small enough that it keeps the hydrogen on the planet. Did you all follow that idea? It's a really interesting concept. The fact that this idea of RMS velocity is directly connected to what type of atmosphere you can have on a planet. And that's pretty powerful. All right, so let's do some problems. Any questions before we move on? All right, so 2 problems here. First one's pretty easy. Calculating RMS and average speeds. This is just a simple kind of statistics problem. It says 5 gas molecules have speeds of 500, 600, 700, 800, and 900. What's the RMS speed and what's the average speed? All right. So to find the average speed, let's do that part first. to find the average velocity, average speed, we would take 500 plus 600 plus 700 plus 800, 800 plus 900, and then divide by 5. I'm pretty sure what we're going to get is 700. Because if you add these all up together, it's going to be 3,500, and you divide by 5, you get 700. Okay. What about the RMS velocity? To find the RMS velocity, we have to take the velocities squared, and we have to average those. So our RMS velocity is going to be 500 squared plus like that. And we can solve that one. So and then divide that by 5, and we get... I did something wrong. 500 squared plus 600 squared, 700 squared, 800 squared. Oh, whoops, I left something out. We have to do that, but then we have to square root it. Right, that makes sense. That number's way too big. So that's the average squared velocity. And if we do 51,000, and we take the square root of that, there we go, that's the answer, 714. My bad. So we actually have to square root all of this, which means we have to square root all of that. Which means we get VRMS is 714. You'll notice they're pretty close to each other. Pretty simple calculation. Okay, next let's do this one. What is the average translational kinetic energy of an ideal gas molecule at 27 degrees Celsius? So I want to kind of get into some terminology here with this problem. So we had this expression. When it says the average translational kinetic energy of an ideal gas molecule, it means this. Okay, that's what this means. So that's the first thing we're going to calculate. Let's just go ahead and calculate it. It gives us a temperature. That's really all we need. The temperature T is 27 degrees Celsius, but we need to add to that 273 to get in Kelvin. That's going to give us a temperature of 300 Kelvin, right? So we can find that the average kinetic energy per molecule is going to be 3/2 times Boltzmann constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. And we multiply that times the absolute temperature, which is 300 Kelvin. And that gives us, so 1.5 times 1.38, it's 38e minus 23, times 300. We get 6.21 times 10 to the minus 21. That's going to be in joules. Sorry, the square is actually supposed to be inside the parentheses. Okay, so that's the answer to the first part. So when you see a question and they ask you for this quantity, that's what you're going to do. Next it says, what is the total random translational kinetic energy of the molecules in 1 mole of this gas? All right, so this is, right here, the kinetic energy for a single molecule. How would I find the total translational kinetic energy in 1 mole of this gas? So multiply by 1. Yeah, we need to multiply by Avogadro's number. That's right. So we have to take our equation and multiply by Avogadro's number. So if we take 3 halves kb times t, and we multiply by Avogadro's number, and then we technically should also multiply by the number of moles, right? It's only 1 mole here, but technically if there were 3 moles or 1.5 moles, we would have to multiply by that as well, right? But remember, kb times Na is equal to something. What's that equal to? You look back in your notes or your textbook. What is that equal to? Nope, that's not right. It's equal to another constant. Scroll back up just a little bit. It's right here. Kb is equal to R over Na, which means Na times Kb is equal to R. So another way that this equation is written, and this is one of the equations we derived last time, is if I take 3 halves times the number of moles times the gas constant, this is equal to, they call it the translational kinetic energy. So this is the total translational kinetic energy of a gas, is this quantity right here. So when they ask you to calculate what is the total kinetic energy, you're going to use this equation here, okay? If you want the kinetic energy per molecule, use that one. Okay? So let's do it. So we're going to get the translational kinetic energy, that's what the TR stands for, is 3 halves times 1 mole times R, which is 8.31 joules per mole Kelvin, times the temperature, which is 300 Kelvin. And so if we do 3 divided by 2, stop it, times, what is this thing? This is stupid. I guess we're not going to use that. 3 divided by 2 times 1 times 8.31 times 300, and push equals. We get 3739. We'll call it 3740. So this is 3740 joules. Much larger number because now we're talking about the whole gas. All right? Okay, any questions? Finally, part C. So this was A, this was B. Now we're going to do C. So in part C, it says to find what is the RMS speed of oxygen molecules at this temperature. So oxygen is O2. O2 is going to have a molar mass that's going to be about 32 grams per mole. You can again look this up on our periodic table right here. You can see that oxygen right here has 16. I don't know how well you can see that. There you go. 16 is the molar mass of oxygen. So if we go back to here, then plugging that into our RMS equation, where VRMS was equal to the square root of 3 RT over the molar mass. Yeah. Then we get VRMS is going to be 3 times 8.31 joules per mole Kelvin, multiplied by temperature, which is 300 Kelvin, divided by molar mass of oxygen, O2, is 32 grams per mole, so we want to convert that to kilograms per mole, which we have to do because there's a joules up here and that has a kilogram inside of it. You get that, and if you calculate this, I think you're going to get 483 meters per second. We'll do it, but I'm pretty sure that's what you're going to get. So if we go to here, move this over to this side this time. So we've got 3 times 8.31 times 300 divided by 32, e minus 3, and then we square root that. Yeah, 483. Should be exactly 1/4 of this. So that was about 2,000. 2,000 divided by 4 is about 500, right? And that's the answer. Pretty easy. We have any questions? Andrew, you said at the beginning of class you had a question about RMS velocity. You feel like you understand it a little better now?
Yeah, definitely cleared it a lot much better.
Okay. Any questions before we move on? Nope. Alrighty. So next thing we're going to talk about are gas molecule collisions. Alright, so up till now, we kind of assumed that the gas molecules don't really collide, but it's a somewhat silly assumption. They actually do probably collide quite a bit, quite frequently, and one of the things we want to figure out is how frequently do gas molecules collide? How far can they travel before they collide? How long can they travel through the air before they collide with each other on average? And we're going to go through a little derivation here to do that. Now, the first thing we're going to do is we're going to imagine that every single gas molecule is identical. It's probably not too hard to imagine that they should all be pretty close to the same. We're also going to assume the gas molecules are spherical. Whether that's reasonable or not, it doesn't really matter. The point is that's the assumption we're going to start with. And we're going to imagine that, at least at first, we're going to assume that all of these molecules, here I'll mark them in like green or something. We're going to assume that these molecules are fixed in place right here, okay, just to make things simple. And that the only thing that's moving is going to be this molecule here that I'll mark as purple. So just this one is moving. All the other ones are sitting still. And we want to figure out the probability that this molecule hits another molecule, basically. And more specifically, how often it happens, right? So what we're going to say is that as this molecule moves forward, if we look at a cylinder that has a radius of 2r, that's double the radius of the molecules, any molecules inside of that cylinder will be hit by this molecule if it's moving with a speed v, and we allow a time interval dt to pass, okay? So it says, in a time dt, a molecule with radius r will collide with any other molecule within a cylindrical volume of radius 2r and length vdt. So we pick dt to be an arbitrary amount of time. It could be 10 seconds. It could be a nanosecond. It doesn't really matter. It's just some interval of time. Don't let the d confuse you. It's just some time interval, right? And we say the distance that this molecule travels in that time will be v times dt, so that kind of tells you spatially how far it's going to move. And it would hit any molecule that was inside of this piece right here, right? As long as the molecule is inside this cylindrical volume, it's going to hit it. So what we can say is that the number of collisions, which we're going to call dn, should be equal to the number of molecules per unit volume multiplied by the volume. Okay, so this is volume down here. I'll make it look like volume. So if we take the number of particles per unit volume, which is basically just related to the density of the gas, right? The density of the gas would be in mass over volume, but you can convert mass over volume into number of particles per unit volume by using Avogadro's number. So this is basically just a representation of the density of the molecules, right? So number of molecules divided by the volume, and then we need to multiply by the volume of the cylinder, okay? Because this is only going to hit molecules that are within that volume, basically, at least within this time interval. The volume of this cylinder, that's easy enough to do. It's going to be the length of the side, vdt, multiplied by pi times the radius squared, but the radius is 2r, so it's pi times 2r whole squared. So that gives us that dn, the total number of collisions, is equal to n over volume multiplied by v times dt times 4 pi r squared. Next, what we're going to do is we're going to divide the dt to the left-hand side. This will give us the number of collisions that occur per second. Times velocity, sorry, divided by volume. This is velocity and this is volume. So this is going to be number of collisions per second. you can see that it depends on if it's a smaller volume, you're going to get more collisions per second. If the molecules are moving faster, you get more collisions per second. If the size of the molecules goes up, you're going to get more collisions per second. And if you try to pack more molecules inside of there, of course you get more collisions per second. 4 and pi are just constants. Now, what we can do as well is we can say that we started off this problem by assuming that the green molecules were sitting still, right? And we just figured out what was happening here. The reality is if they're all moving, it's going to increase the number of collisions per second, and we have to just take the book's word for this, I guess, I don't know, by a factor of square root 2. So if they're all moving, we need to multiply this by an additional factor of square root 2, apparently, in order to get this to be correct. So we have to just kind of take the book's word for this. The other portions of this I totally understand. This part it seems reasonable to me. But why it's exactly square root 2, I don't actually know. I have to do some more research. Anyway, so the next thing we want to figure out is the amount of time that occurs per collision. Okay? So if we want to know the time between collisions, this is what we're going to call the mean time. And it's going to basically be equal to dt over dn. So it's the reciprocal of this. So it's going to be volume divided by n, 4 pi r squared, velocity, and then root 2. That's going to give us the mean time between collisions, right? And now, the next thing we'd like to figure out is how far the molecules can travel before they collide with each other. So how far can a molecule travel, on average, between collisions? And for that, all we need to do is say, well, if this is the time, let's say it's 10 seconds. Let's say the mean time is 10 seconds between collisions. That means there's a collision occurring every 10 seconds. Then how far can an average gas molecule travel? Well, it would be whatever the velocity of the molecule is, multiplied by the mean time. And we call this the mean free path. Okay, we're going to call it lambda sub mean. We call this the mean free path. I'll label it on the next line. And if you look at what happens, if I multiply velocity times this equation, it basically cancels out with that velocity. So you end up just getting volume of the gas divided by n multiplied by 4 pi r squared times the square root of 2. So if you're asked on an exam to find how far a molecule can travel between collisions, you use this equation. If you want to know time between collisions, you use this equation. And this we call the mean free path. Now, I don't know for sure if this is going to trip anyone up in the future, but I do know I remember talking to Dr. Corneas, and he told me that people tend to get this a lot wrong on exams. So it's something that's actually pretty easy to do. We'll do a calculation here in a second, but you can see it's just a pure plug and chug kind of thing. All you need to know is the radius of the molecules, which you're going to have to be given, right? You need to know the volume of the gas, which again you'd have to be given, and you need to know number of molecules. And that's it. And you can calculate how far a molecule can travel between collisions. And we'll see just how big this number might be or how small it might be here in a second. All right, that's that. Anyone have any questions? We can write this in a slightly different way. We can put pressure and temperature in there if we want to. And the way that we can do that is by considering the fact that we have these two versions of the ideal gas law. One of them is PV is equal to nRT. The other one is PV is equal to, I don't know if we've talked about this one yet. I think we have, N times the Boltzmann constant times T. These are the same thing because if you look at just this piece right here, N times R. So little n times R is also equal to, remember that R is equal to Kb times Avogadro's number. So this is also equal to N times Boltzmann constant times Avogadro's number. But if you take the number of moles and you multiply by Avogadro's number, which is the number of atoms per mole, then you get, when you take number of moles times Avogadro's number, I guess just as a test to see if you're all still with me. What do you get when you do this? number of moles times Avogadro's number. What do you get? Nope. Total number of molecules, and that's what we've been using capital N for, right? So that means that little n times r is also equal to n times kb. These are the same thing. So you can replace nr in the ideal gas law equation with n times kb. And then what we can do is we can look at this equation here and see it has volume divided by n, right? So if we rewrite our equation and write volume divided by n, right, that should be equal to Boltzmann constant times temperature divided by pressure. So we can then rewrite our lambda mean expression to be equal to k times t divided by n 4 pi r squared times pressure and then times square root 2. That's another way that we could write this. All right. But of course, this would only work for an ideal gas. As you'll find out, we're going to treat a lot of things like ideal gases. All right, so 2 different definitions of mean free path. Make sure you understand both of them. And let's do a problem. Let's look at this picture and talk about it, actually. It says, if you try to walk through a crowd, your mean free path, the distance you can travel on average without running into another person, depends on how large the people are. It also depends on how big you are and how closely they are spaced. So if you're walking around in downtown New York, or you're walking through, let's say, a concert venue or something like that, where everyone's kind of packed closely together, you're probably going to bump into people when you kind of move around, right? As people spread out, if you go to the library where people would tend to be very spread out, you probably don't bump into people very often. But yeah, that would be your mean free path. How far you could travel without bumping into somebody else. Maybe that helps you to understand it. All right, so this is what we want to do. I guess we'll leave the problem down here and just write in this space so that we can keep these things up here. All right, so it says estimate the mean free path of a molecule of air at 27 degrees Celsius and 1 atmosphere of pressure. Model the molecules as spheres with a radius of 2 times 10 to the negative 10 meters. So we have a temperature of 27. We add 273 to that to get 300 Kelvin again. We have a pressure that's equal to 1 atmosphere. And we say that the radius of our molecules is 2 times 10 to the minus 10 meters. Very tiny distance. It's 0.2 nanometers. Super, super small, but molecules are small. It says to find the mean free path. So let's do it. Mean free path is, we're probably going to use that equation, right? So KB is 1.38 times 10 to the minus 23, joules per Kelvin, right? Temperature, 300 Kelvin. Number of molecules in, what do we have for number of molecules? Oh, I made a mistake. What's the mistake that I made right here?
You didn't cancel out n.
Yep, that's right. This n should not have been here. That's the correct equation. So be sure to change that if you're taking notes. Not that. That should still be a 4. But yeah, V over N. We were replacing V over N here. So the N should have disappeared, right? Okay, so KB times T divided by 4 pi times R squared times the pressure. Except if this is in joules, I need to convert the pressure to pascals. But that's easy to do because 1 atmosphere is 1.013 times 10 to the 5 pascals. And then we have square root 2. Oh, and we have the radius, so let's actually plug that in there. We'll just put 4 pi, we'll put the radius squared on the end. So times radius squared is 2 times 10 to the minus 10 meters, and then we have to square it. And that should give us lambda mean. So as you can see, not too tricky. pure plug and chug, as many of the problems in this class are. All right, let's do this. Oh, that's nice. Okay. (5.7 times 10 to the minus 8). Why don't you all do that calculation too, and tell me what you get. No, that's not right. No. It would be... You all got the same answer? All right. This would actually be like 57.5 nanometers. Not very far. Not very far. Can travel like a few radii, a few thicknesses of the atoms themselves before. Yep. All right. Any questions? Okay. Part B says to estimate the mean free time of an oxygen molecule with V equal to VRMS at 27 degrees Celsius and 1 atmosphere pressure. To find mean free time, we saw from above that V times T mean is equal to lambda mean, so we can start from there. So the mean free time multiplied by the velocity is equal to lambda mean, which means that the mean free time in this case should be equal to lambda mean, which we calculated to be 5.75 times 10 to the minus 8 meters, divided by the velocity. In this case, we're going to use RMS velocity. So if we divide by the RMS velocity of an oxygen molecule at 27 degrees Celsius, we already calculated that in the previous problem, and it was 483 meters per second. Right here. So same temperature. That's all that matters, and it's oxygen. Right? So we just need to take the distance that we just got and divide by 483. So I'll do that right here. And we get 1.2 times 10 to the minus 10 seconds. A very, very short amount of time. That is approximately 0.12 nanoseconds. That means there's collisions occurring pretty much constantly. Pretty much constantly, there are collisions occurring. All right, anyone have any questions? You know, another way we could write this would be 0.06 micrometers. And I mention that because I believe that 1 micrometer is about the thickness of your hair. Everyone's hair is different, but let's say just on average. I think the thickness of the human hair is like 1 or 2 micrometers. So to say that the mean free path for these gas molecules is 0.06 micrometers means that, I mean, that's like, what is that, like 1/20th the size of a human hair? So if you can imagine cutting your hair into a 20th, which is pretty hard to imagine, you get this really tiny, slender piece of hair. That's about how far these molecules actually move before they hit each other, which tells you that they're not moving very far before they start hitting things, right? We think of gas molecules as being very spread out, and they are, but they're all moving at the same time. So when you have a huge amount of gas molecules and they're all moving at the same time, it's very likely that two of them are going to hit each other, right? Because you've got this one that's traveling through the air, and there's just all kinds of things that are zipping around it. It's eventually going to hit something else, right? Okay. And of course, once it hits something, its velocity changes, right? It's going this way, it hits something, it's going to go back this way, or maybe it goes off this way, depending on how it gets hit. Okay, so this is a pretty good place to take a break. Are there any questions?